So with nuclear changes, they frequently involve large amounts of energy. And again, alpha and beta decay are the two common ones that change the identity of the nucleus. Alpha decay, we know, decreases the atomic number by 2. Beta decay increases it by 1. And gamma radiation usually accompanies alpha and beta decay and also nuclear fission. Gamma radiation can be quite harmful to humans, and that's what you need to detect if you were working at a nuclear power plant. Nuclear fission involves a single nucleus breaking apart, and nuclear fusion involves two nuclei combining to form a nucleus with a larger atomic number. Nuclear fusion takes place in extremely hot environments, such as the core of stars, and it's very difficult to have that happen and occur on Earth because of that high temperature. Okay, you could get it to occur, but then there wouldn't be much Earth. So you could get some gold out of it, but you'd have some problems. Now, to form elements. If we look up here, it says, shows these two owls trying to make some gold. Okay, what patterns do you notice in the fusion reactions up here on the picture? Any patterns you see, just raise your hand. Tell me what you see. One pattern, yeah? See one? Yeah, what is it? Okay, elements form energy. Excellent, yes? All of them got helium in there somewhere. Good. Any other patterns you see? Energy in all of them. Excellent. Good. What else? Anything else you see? Yeah? Uh-huh. Excellent. Okay. Excellent. All right. Do you think gold can be created on Earth by a fusion reaction? No. Why not? That's what? Not hot enough. Very good. Temperatures. Now, what if we could get the temperature and we didn't destroy the whole Earth? Would it be possible to create gold if we could raise the temperature high enough? Yeah. What does this so on mean? Keep going. So we go, bam, here, to there, to there, to there, to there, to there, to there, to there. Up there we go, very gold. So the question is, would that work? Would that happen? And we got some limitations, it sounds like, already. Yeah. All right, these are only the even ones. So what about the odd ones? Where do the odd ones come in? How do we get the odd ones? All these are even ones. So what's happening in this situation? Now, our sun happens to be made up of mainly hydrogen and helium. And the helium combining is what we see in this pattern here. So one option is hydrogen can be involved with it, possibly, and that could change it to some of the odd ones, or there could be something else that causes them to change. For example, if we had oxygen here, and it went through beta decay, it would become chlorine. That's an option, possibly. Not fusion, but that's a different option that could happen. So we're going to look at how new elements are formed, and if it is possible for them to be formed here on Earth, and how do we know? So to look at this, we're going to be able to explain how different elements are formed through nuclear reactions. We'll be able to write a balanced nuclear equation and describe the mechanisms behind a nuclear chain reaction. So, to do this, we are going to be working individually. Before we do this, though, I want to show you an example of a nuclear equation. Nuclear equation. So these are referred to as nuclear reactions or nuclear equations. These might be 3 ones to write down as good examples on your notes. So the first one up here, it does not give us a lot of information and gives us a lot of blanks. So the first one up here is uranium, and it is spontaneously breaking down, okay, into 2 things. This process is called a nuclear fission reaction. And in this particular case, you would have to be told how it reacts. So in this case, uranium is going through what's called alpha decay. Sometimes it's called alpha emission, or emitting an alpha particle. So uranium, some information about uranium you would need to know to fill in this nuclear reaction is uranium has a mass number of 238 and an atomic number of 92. It's emitting an alpha particle. So when we see alpha or the word alpha, that means 42He. So it's emitting an alpha particle, which goes in here, 42He. The uranium is called the parent isotope, and we do not know the daughter isotope. That's the question. So to determine what goes in this blank for the daughter, if you're told uranium-238 goes through alpha decay, what you do is you look at each side. In order for this to work, you've got 238 on the left and 4 on the right. 238's on the left, that equals 4 plus something. I don't know what. So, using algebra, we can solve for this unknown x. What would x have to be if 238 equals 4 plus x? 234. We subtract 4 from each side, we get 234 equals x. It's going to be mass number of 234. So you look at the top, they have to equal on each side. Then you look at the bottom. The bottom has to equal on each side as well, because you can't lose or gain mass or matter in chemical or nuclear reactions. So you got 92 on the left. This equals 2 plus some unknown y. I just chose y because it's after x. So what would y have to equal? Y would have to equal 90. Now, that's the atomic number. The atomic number tells you the identity of the element. Number 90 on the periodic table is element TH. You don't have to even know the name of it, but TH is the daughter isotope. It happens to be called thorium-234. Yes, sir?
How do you know it's alpha decay?
You would have to be told that, or you would have to be given more information. Yeah. So I'm just giving examples. The first one is alpha decay. You have to be told that in order to get the 42He. Alright? Now, the second one, you got BA. BA is going through some sort of decay as well. I'm going to use BA as an example of beta decay. So, you would have to be told it's beta decay. You can't just look it up on most of these things. So, a barium, if I use barium straight off the periodic table, barium has an atomic number of 56 and a mass number, mass number 137. So we'll use barium 137, and we'll say it goes through beta decay. A beta particle is a 0, an electron, 0 mass number, and -1 is its atomic number. It's got a charge of -1. So when you lose that electron there, 137, do the little math, 137 equals 0 plus x. So x equals 137 on the top. And then on the bottom, 56 equals -1 plus y. So doing our math, please tell the person next to you what number you think goes in the bottom for this daughter isotope. All right, so we got a couple options. We got 55, 56, or 57. So how many think it's 57? Hands up. 57 is correct. 57 minus 1 equals 56. You add 1 to each side, 57 equals y. So watch the math on that one. That's the trickiest thing you possibly have in beta decay. Remember, it goes up by 1. So barium goes up by 1. It becomes La, which is lanthanum. This is the daughter isotope, La. And it should agree with our observations. So that's beta decay. An example of that. These two are called nuclear fission. If I look at the bottom, what is this an example of? Nuclear what? Fusion. So just to double check, the numbers should match. If I quickly look at CR is number 24, HE is number 4, 24, whoa, sorry, wrong place. HE is number 2 today, 24. All right, 24 plus 2 equals 26. That should be the atomic number for iron. The 42He, what is this also called? An alpha particle. But this one is not being decayed. So this is called alpha particle. Sometimes it's called absorption. Or capture. It's a nuclear fusion process. Sometimes alpha particles are the ones that are fusing together. Not always. Not always. This is just one example. You could have other elements fusing together. Yes?
How do you know if it's decaying?
Decay usually is nuclear fission, and the small particles will be on the right. Yep. So it's called decay when it's breaking apart. It's called fusion, capture, or absorption when it's coming together. Usually, the bottom one is always called fusion generically, because there's all sorts of different things that can fuse together. The top one with an alpha particle, that's alpha decay, because it's an alpha particle emitted. It doesn't matter what the parent or daughter is. And the middle one, it's beta particle, because that's what's emitted always in that particular type of reaction. All right, so at this time, if we look at lesson number 16, what you're going to do is you're going to work with some nuclear equations to see how the reactions proceed. You're going to work individually. You may use your calculator, your isotope chart from lesson 14 as needed, and your periodic table as needed. So we will have about 10 minutes to work on this. And then we'll talk a little bit about what we see, what patterns we see.